Okay, so continuing this talk about did Viking discover life back in the 1970s? And we got as far as halobacteria, which is able to survive in the Atacama Desert using deliquescing salts. And then the phoenix observation that the legs of phoenix, that you got these drops that seem to form on the legs. And they weren't able to actually look directly and see what it is because it wasn't planned. So they couldn't analyse what's going on. But what happened is you got these things that are dark and they look for all the world like droplets of some liquid. And the salt, they think what happened was the salt was thrown up onto the legs of the phoenix when it landed. And then the salts took in water from the atmosphere in the humidity at night. And they gradually grew and grew and grew. And then you get these drops, they merge together, and then finally they disappeared. Suddenly they disappear and it's not there anymore. It's thought that the drop probably fell off. And then they don't form again. So that means this all looks very much like what you'd expect from deliquescing salts, that the salts deliquesced, the drop fell off, the salt was gone, so they couldn't form again. However, being proper scientists, you can't really say this confirms that there was deliquescing on Mars, because it wasn't possible to analyse it and see actually what was going on. But I don't think anybody's got an alternative hypothesis for it. And then the other thing that Phoenix discovered is that through its isotope measurements, then it found that the oxygen in the atmosphere, and so carbon dioxide in the atmosphere comes from volcanoes, and you can get this detection that it must have been replenished in the fairly recent geological past by the isotope ratios of the carbon, and by the isotope ratios of oxygen, then it turns out that it must have exchanged oxygen with something on the surface, most likely water. So this is indirect evidence of water. However, the water could have been occasional impacts on the poles of Mars, and but the other possibility, and it seems quite favourable, is that there's actually a thin layer of these deliquescing salts all over the surface of Mars. And then it would depend on the composition, so whether it's sulfates or it's perchlorates, or then the mixture of the two, and whether it's sodium or potassium, as to where they would most favourably take in water and what temperature would be at and how much water activity there is. And it could be it's too cold, it could be it's too dry, but somewhere in between the two you could get water that life can make use of. So then you get the idea, and it's a paper that's independent of the Mars labeled release experiment. This is a paper, the idea of advancing sand dunes by a reactor. So the idea there is that that you have these salts in maybe no concentration, but you have these salts actually in the sands of Mars, and as these sand dunes go over, they would churn up the surface, and these salts get in there, and then the microbes, it would then deliquesce, get a little bit of water, just enough for life to be able to survive, just maybe a few cells here and there amongst the sand. So that seems quite promising for Viking, because it wouldn't be very obvious, and yet there would be enough life there so that it would be able to make these, so actually you'd have a few cells, enough to be able to start reproducing. So that would be one of the things that hypotheses that you dust off if you're wondering, trying to explain how there could be life at the Viking landing site. And so this basically might be halobacteria or something like that. Some organisms able to tolerate very salty and very cold conditions also is best. And so there's certain extremophiles that can tolerate both cold and salt as well. And then you could be using the deliquescing salts. Cold is best, not just, although it's warm on the surface, it wouldn't stay liquid for very long if it was quite warm. So better if it can tolerate cold a little bit below the surface. So that's that idea. Then the other idea is the idea that the life could actually take the water vapour directly from the atmosphere. So instead of relying on the salt to deliquesce, then it just takes the water directly, just the way the salt does. And again, all of this is very promising because of the photographs that Viking took, and they actually took photographs of a frost. So you get frosts in the landscape, even in equatorial regions, because of the very high humidity at night. So there's the water vapor available in the atmosphere. Well, in rather similar conditions on the Earth, then you get microorganisms and plants, so multicellular plants as well, lichens, that are able to do it without any water at all. And this is in the permafrost areas, so in the areas of the tundra, and in the very high up in the mountains. Then you get lichens, and you also get certain microorganisms that can just take in the moisture from the atmosphere. And the 100% moisture that you get when it's cold. And so this is very promising as a model of something that could work on Mars, because you don't need any water activity, and it doesn't matter that it boils at 5 degrees centigrade if you're just taking in moisture in from the atmosphere. And so this led the German aerospace company, DLR, and they've sponsored a whole series of experiments on this. And so they took these lichens and they put them into a Mars simulation chamber. So it was simulating the Mars atmosphere, simulating the day-night cycle, simulating the strong ultraviolet radiation as well, which is quite a challenge, especially for photosynthetic life. So if you're talking about lichens on Mars, it would be exposed to high levels of ultraviolet light. But these lichens do have protection against ultraviolet light, even on the Earth. Even though it's nothing like the ultraviolet radiation levels of Mars, still they have some protection, and it's just like the way human beings have protection against ultraviolet light. So that's why you tan, and that's why some people have dark skins, to protect from ultraviolet light. And so in these lichens, they have a similar mechanism. They actually use melanin, the same as humans do. They also have a couple of other chemicals. One of them is called eugenic acid, which is peculiar to lichens and doesn't occur in any other species, on the Earth that is anyway. And so what happens is, instead of the ultraviolet light breaking up the cells, they get absorbed by these other chemicals instead. So it's quite easy to shield out ultraviolet light, just a thin sheet of paper even. If you've got a shadow, then that's shading out ultraviolet light. And so it's not too difficult, if the cells evolved in that way, for cells and for lichens to evolve in such a way that they can cope with ultraviolet light. So this is not the full ultraviolet light. Full ultraviolet light and the full sunlight on Mars, it's really quite hard to, some microorganisms can tolerate that for hours actually, and even a bit longer, but it's really quite hard to tolerate full sunlight. So in the Mars simulation chamber, they survived best in partially shaded. So places where you get light part of the day at an angle, those sort of places. And then another way in which you could get it is if you've got just below the surface of the soil, because the Martian sand, it's iron oxides, it's quite good at shielding out ultraviolet light. And just below it, you get places where there'd be partial light with not very much ultraviolet light, where you could get photosynthesis just within a few millimeters of the surface. You could also get photosynthesis underneath the surface of rocks, if you have little transparent inclusions in the rock. That is the way you get photosynthesis happening in the Atacama Desert in such circumstances like that, so that also could happen on Mars. So these are all possibilities, so as long as the life can get what it needs, mainly from the atmosphere. And so we're looking at water particularly at this point, and also carbon dioxide. So photosynthesis, it relies mainly on carbon dioxide and water, and it uses light as its energy source, so it's rather minimal in its requirements. And these lichens in the Mars simulation chambers, they did just as well as they did in the Earth's atmosphere. They didn't seem to be bothered by the very thin atmosphere, and they didn't seem to be bothered by the ultraviolet light either. And to all, as far as they could tell, with a rather short experiment of a few weeks, so they didn't do very long experiments, they're gradually doing more and more experiments on this, then as far as they could tell, then it was just metabolizing normally, and photosynthesizing. It was doing active photosynthesis, it was doing active metabolism, and it seemed to be going normally in the simulated Mars atmosphere without any water at all, just the moisture in the atmosphere. Now, lichen is of course a very slow growing organism, so they couldn't really confirm very well this, you couldn't like take it through its entire life cycle or anything like that in just a month or two. But it's ongoing experiments, and it does look very promising so far. So that would mean that if that was possible on Mars, and if Mars life had evolved this capability, and so that's a big question, whether it's possible and then whether it actually evolved it, then you could have life almost anywhere on the surface of Mars. Then it gets really rather easy to explain the Viking experiments. And so then the one remaining question there is that life on the Earth, it also needs nitrogen. It doesn't just need carbon and water and oxygen, and of course trace elements, but you could get those from the rocks. But the big problem is, where can you get the nitrogen from? Now, of course, life on Mars, it could be completely different from life on Earth. It doesn't need to be based on DNA or proteins or enzymes in the sense that we have it on Earth. But the exobiologists, they think theoretically that life very likely would have some kind of informational molecule like DNA, even if it's not DNA, but some molecule, and probably built up using amino acids, because that would be the ingredients that would be readily available on the early atmosphere, but not necessarily. Just seems quite likely. And it's also thought that it would have that just carbon. If it was just carbon, so carbon bases in water seems very likely. And then if it's just based on carbon chains without any nitrogen, the problem is that the carbon is very well bound to each other. And then you just get some kind of like tar or something, you get some kind of thing which is just a sticky mess. And it's very hard to see that working as actually getting it, actually getting the whole process of it reproducing and making transcription and so on like that, if all you have is the carbon and hydrogen and oxygen. So the main problem is that the carbon is so tightly bound to each other and it can't be split apart very easily. And nitrogen is much more lightly bound to carbon. So this apparently is the reason. I'm not a biologist myself, so I'll give you some links so you can go and follow this up if you're into the technical side of these things. But the biologists, they reckon that we need nitrogen in order to have some intermediate bond between the bonds just using hydrogen atoms and the bonds from carbon to carbon, an intermediate strength of nitrogen, in order to get all the delicate machinery of cell machinery and cell reproduction and this sort of stuff going on. So we just have to suppose that's right. I don't know, it might be disproved, but it seems exobiologists, they seem pretty clear that this is needed. So if nitrogen is needed, then the question is, there is some nitrogen in the Mars atmosphere, but it's very little of it, 0.2 millibars, compared with 720 millibars in the Earth atmosphere. So tiny, tiny amounts of nitrogen. But Mars had nitrogen, a lot of abundant nitrogen in the early solar system, I thought. The best hypothesis is rather similar to Earth. And the nitrogen turns into nitrates through fixing, not just through life. So in the case of the early Mars atmosphere, for instance, the main process that did fixation of the nitrogen in the early atmosphere, the theoretical studies suggest anyway, are the actual impacts themselves. So when you get huge impacts onto a planet with a nitrogen atmosphere, you get lots of nitrates forming in their models. So there may very well be thick deposits of nitrates on Mars. Rather similar, though for different reasons, that in the Atacama Desert you get thick deposits of nitrates which are quite a bit below the surface because nitrates are very soluble. So the Atacama Desert, although it seems so inhospitable, was at one time the premier place to go to get nitrates before the inorganic methods were developed. So they used to go there and mine nitrates for fertilizer. Completely inhospitable on the surface, but deep below it has these very rich deposits of nitrates. Well, Mars could be like that. So that's one possible way you could have nitrates. And then another possible way you could have nitrates on Mars is that, and fixing of nitrogen, is that the various processes of volcanic processes and lightning and the various processes that create nitrates. And for instance, in the McMurdo Dry valleys in Antarctica, then the nitrates that they primarily rely on nitrates that come from atmospheric processes such as that, and various chemical processes in the higher atmosphere of the Earth. So it could be similar on Mars, that there are atmospheric processes that are producing a tiny, tiny amount of nitrates, but enough so there's enough for life to go on. And basically it's because of the nitrogen that you wouldn't expect to find lichen, and the difficulty of finding nitrogen. That's why you wouldn't expect like every rock to be completely covered in lichen and green algae and something. Then it's likely to be a little bit sparse because of the difficulty of accessing the nitrogen. So, but there are possibilities, and there's also meteorites. Some meteorites have nitrates on them, so this can deliver smaller levels of nitrates to the surface of Mars. And then there's another process that is very useful for the equatorial regions, like where the Curiosity and where Viking is. And this is if you could get very thin films of water over the surface. So if you've got this deliquescing, then you can also get very thin films of water. In certain circumstances, very thin films of water, you get nitrogen fixation happening within a molecular levels, just a few molecules thick films of water. So that's another form of nitrogen fixation. And then another idea is just something that it's like an obvious idea, is to think, could the life get the nitrogen from the atmosphere? So I've tried to find out and see if there are any papers on this, because if it could, then we literally could have life almost anywhere. The problem with that is that, of course, there's so very little, just 0.2 millibars. And so I had to look. There's only one paper that I've been able to find. And this is quite an old paper, and it just looked at ordinary nitrogen fixation using microorganisms such as they use for study of nitrogen fixation whenever you want to study it. So nothing special, no extremophile, nothing very special. And these microorganisms, they could go down to 5 millibars. However, they couldn't go all the way down to 0.2 millibars, and the experiment just says that they could manage down to 5 millibars, they couldn't manage below 1 millibar. They don't say what happens in between the two. So that seems really rather close to our 0.2 millibars. You sort of wonder, could some extremophile be able to just do the extra step? So I've gone down from 720 all the way down to 5. Could it go down to 0.2? And I'm quite surprised to find there doesn't seem to be anything in the literature about this, except one other experiment, one paper. And this paper is a couple of papers, and the second one says there's intermediate results and more research needs to be done. They don't seem to produce the third paper as far as I can find, so I'm going to try and chase that up and see if I can find out more about that. But what they did is they found, they looked at more exotic microorganisms, and they tried them in a Mars-simulated atmosphere, and they got visual indications which seemed to suggest that there was nitrogen fixation going on. And they were needing to do follow-up experiments to check if it actually was nitrogen fixation. So that's rather tantalizing, because I couldn't find any follow-up experiments. So I don't know if they're going to do them, or they never did it, or it never got completed, or whether this paper exists somewhere and it's just hard to find. So I'm going to try and find out the answer to that. Anyway, so that's certainly the slender possibility, and nobody would say that any of this is very probable, but there's a slender possibility that there could be life even in the Viking area. And if you go there and you actually find life there, then you would say, well, it must be some ideas like this. Now, there may be other ideas as well. I've probably left some things out, but these seem to be a couple of the two main reasons why you might think there might be life there. I'm very interested in any comments as to what you think, and have you come across any research on this? And does anybody watching this know anything about whether nitrogen fixation is possible in the Mars atmosphere? Any more research except this ancient paper? And just like to say in conclusion that I think the labeled release is an excellent experiment, and these were good researchers. They did a very good job of designing the experiment, And I think they were simply unfortunate. Nobody could have predicted that the Martian at the surface was so very different from Earth, and with this unusual chemistry. And I'm sure that if they'd known about that, then they would have designed the experiment in such a way as to try and eliminate these problems. And he actually has, Gilbert Levin has these ideas for a follow-up, which would be looking at chirality, and then there's all these other experiments that we could do, we can send to Mars. Hopefully ExoMars will make a bit of a change in 2018. So we're not likely really to learn too much more about this until 2018, when just the possibility that ExoMars might find something, but it doesn't have labeled release. And if it doesn't, but it would be able to detect very small concentrations of organics, so tiny levels, so that could be a help. And we might learn a little bit more then. And also be able to test for chirality and biosignatures. And then maybe eventually, I do very much hope that we find a way to send a labeled release to Mars, along with many other experiments, so that you get more sensitive equipment, such as we didn't have on Viking, but it was obviously the right way to go, to have just not the labeled release on its own, but lots of other experiments as well. The only problem was, with Viking, was that the other experiments were not sensitive enough, because they were expecting that if there was life, it would be pretty easy to spot it. And we now realise that there could be life there, that it's very difficult to spot, very, very difficult to spot. And so we need extremely sensitive, if it's present-day life, even if you're right on top of the actual habitat. And then the other thing, just one more thing to say, is just that if they don't find life in equatorial regions, then this is the least likely place to find life. It still seems a very good chance of finding life somewhere else on Mars, such as the warm seasonal flows, for instance, or the Martian geysers, the hotspots where you may get greenhouse, the warm greenhouse effect of water melting beneath ice, as well as the carbon dioxide. And there are quite a few different places, and of course the deliquescing salts beneath the surface. Anyway, it's exciting times, and maybe we'll find some answers within a few years.